All right. So just all of you out there know we are recording. A few things too that we noticed. One of the things we really would like you to do before you go over this with us is do the self-score, okay? Go through the rubric and to the best of your ability, try to score yourself, because that is also something we can help you with here today, is if you're like, would I have gotten this point? We can try and take a look at that. We understand that you might get to something and you're not sure exactly how to score yourself. And when you do score yourself, that's not going to be counted as part of your grade. Like if you give yourself a 1 out of 10 or whatever the points are, we're not going to be like, well,
you get a
1 out of 10. And if you give yourself a 10 out of 10 and you didn't do anything, we're not giving you a perfect score either. So we'll talk about the participation trophy a little bit more in class today. You do got to earn your participation trophy by
finishing the race.
Participating. So, okay. Let's take a look at this one. Where am I here? All right. So we have the amusement park ride bench. Okay, we had a good question. Why is it not just say Ferris wheel? But these questions are given worldwide. And if English is not your first language, you might not know what a Ferris wheel is. So amusement park ride, I think they think is a little bit more generalized. But the first thing I notice here looking at this problem is, okay, well, we've got some rotation. Okay, so maybe we're going to be looking at rotation. I'm thinking maybe about centripetal forces. I also know that the object is going from a down position to an up position. So there is even consideration of energy going on here. So just a few things that kind of go through my mind when I first look at this problem, okay? So passenger compartment of rotating amusement ride contains a bench on which book mass MB, all right, well, that's probably gonna be important, is indicated by the dot in the left figure above. All right, so that's it right there, fantastic. The compartment moves with a constant angular speed. Okay, so one thing I'm gonna say is make sure you understand the difference before you take the AP test between speed velocity and acceleration. Because what a lot of students do, and most of you aren't doing this anymore, but they see something that says constant acceleration and they go, oh, constant speed. No, constant acceleration means something is changing, okay? Now, it is possible to do a constant speed with constant acceleration if we're just turning, but don't get thrown by that on the AP test. So I go, okay, constant angular speed. So we got our funny looking W here, omega, okay? It's going about the center of the ride, circular path of radius R. Whoops, that's not what I wanted. The bench remains horizontal throughout the compartment's motion. Okay. The right figure above shows a magnified view of the compartment. Okay, fantastic. Hey, a graph. First thing I do, I see a graph and I go, what information can I get from this graph? And I go, it is a position versus time graph. And so I go, all right, what do I know about position time graphs? It tells me where an object is at a moment in time. That's what a point tells me. The slope of this graph, what's that going to tell me? Velocity, right?
Velocity.
Absolute value would then give me speed. Okay. Area. What was it?
Total.
It doesn't tell us anything useful. Okay. You don't have any formulas that are going to be x multiplied by t. All right. So the area does not tell us anything useful, but I do know that the slope is going to be the velocity. So these are just little things that I'm making note of before I even know what question they're asking me. I also look at this and I go, hey, it's one of those wavy graphs. Might be dealing with some sort of simple harmonic motion ideas here, okay? But it turns out, in this case, is it simple harmonic motion? So this is a good question, because this is where they're giving a graph that looks like one of those, right? But it's a little bit odd. It's not simple harmonic motion in what we're used to, where it's a pendulum going back and forth or a spring going back and forth. This is kind of a weird one. It's the x-axis motion. And this does end up going back and forth on the x-axis, right? So you can look at it from a simple harmonic motion point of view. It's just a little bit different than what we are used to, okay? All right. So finally to the first question. It says, and actually I should highlight that. And it is that horizontal component of the book's position, okay? Which is a little bit weird. All right, determine the period of revolution of the book. Okay, well that means you need to know what period stands for. And so period is the amount of time to complete one full cycle. And we should be able to get that from one of these graphs. And from the papers that we did look at, I think everyone was pretty much like, hey, I can do this one. There was a lot of people that got this one right. So I'm just going to say, all right, when does this start to repeat? Now, the only thing to be careful with here, if you choose this point, is if you go to this point and say, oh, it starts to repeat itself. Because this is a down, you also need an up in there. Okay, so you got your down and your up. And so this is the point we're going to over here. And then it's just a matter of making sure you read your graph properly. So I'm going to count, okay, I got 1, 2, 3, 4, 5. 100 divided by 5, last I checked, was 20. And that should mean that this in here is 120. Time is in seconds. So I'm going to say period equals 120 seconds. Okay. This is a tricky one in terms of, do I need to say anything else here? A lot of times in AP Physics 1, you do need to give some sort of explanation. In all honesty, I think this was actually a question that was stolen from maybe AP Physics B. I don't know that for sure. And they're not really looking for much more in terms of an explanation. This is going to be, my guess is a one-pointer, you get it or you don't. All right. So I wish I could give you better advice on how to determine how much you need to say. Usually though, a problem will say something like justify your answer or something like that if they are expecting you to do more, okay? And I think expecting you to do more is more typical than just a problem where they say, what's the answer? Put it down, okay? It's a little atypical in that sense.
I would say make sure they put seconds after it.
Yes, and do not forget your units if they are giving you a numerical thing to do. You will get penalized most likely if you don't. All right.
Because it will take 120 seconds or 2 minutes. So if you just wrote 2 down, you're good.
Right. And also notice, I made a full mathematical statement here. I didn't just say 120 seconds. I said T equals 120 seconds. Be formal with the person that's going to be looking at your paper. All right. So these are little things to be keeping in mind with the AP test. You may think that Mrs. Schrader and I are horrible people and we grade things pretty tough. They make us look like babies. Okay. They're definitely more picky about things. Okay. All right. The next one, calculate the tangential speed, not the angular speed. Can throw you off a little bit here because even though the answer is not the angular speed, we actually want to use that essentially in our response. Okay. There's a few different ways you can approach this one. I'm going to come down here where I have a little bit of a blank spot here. You can look at this and say V equals distance over time. And since we have a constant angular speed, we have a constant speed. And you can just say that that's going to be 2 pi multiplied by the radius divided by time. And so you can just write 2 pi capital R over period in this case. All right. In a lot of problems, they don't give you numbers. Here, they are telling, I think we do have the 120 seconds. They did not give us a value for R, did they? If I remember it. Oh, yeah, you're right. Thank you. So we go to the graph. And they do want, so this is a little tricky. My guess is they're going to give us points for getting that far, but we're going to have to finish up and get values for
Not
R
yet.
and T.
You have to substitute for R and
Right.
T to get your points.
We don't get any points even for saying this?
No.
Jeez, they're being really picky on this one.
We have to put R value. 'Cause I
Yeah.
just said
If you
You're not
don't
gonna
get the
this-
R
this
value,
point here, so you only get 1 out of 2
I
points.
thought it was because after.
Yeah, so you'd still get 1 out of 2.
very easy to see that that might be what happens though.
Sorry.
Because
I would
getting
say
R
1 out
from
of
the
2.
graph, ooh, that's a little bit tricky.
If any of you guys want me to look at what you have written down
Okay.
for it, please let me know.
If I didn't simplify 2 pi over 120, is that still one
Okay.
point?
So
What'd you do?
2
I left it as 2 pi over 120 instead of pi over 60.
That should be fine.
Yeah,
I think
it
that's-
says equivalence.
Yeah.
So 1 point there.
All right. So horizontal
But you're
position.
still only gonna get 1 point.
When does this thing reach its maximum horizontal position? Well, right here. And that's how we know that the graph is going to tell us R. Okay. That's a little bit hard. So it looks like we have an R value of 30 meters. This is a big Ferris wheel. Like that Navy Pier one.
Yeah.
And so we just get V equals 2 pi times 30 over 120 seconds. I'm being really formal here. You might not need to write all the units and stuff like that in there. But we have 60 pi over 120 meters per second. So the question in here was, how much do you have to simplify and still get credit? Honestly, they're not terribly nuts about simplifying. Okay. My guess is you would actually probably get credit for this. All right. But as long as I'm doing my math well here at 9:20 in the morning, this is pi over 2. Yeah. Thank you. And if you wanted to do 3.14 divided by 2, roughly 1.5-ish meters per second, that should be fine
The
too.
rubric says pi over 2 or 1.6 are acceptable.
Yeah, don't round pi to 3 in this case. So,
Yeah.
because it's more like 1.55. So,
Do you want us to go into this, like looking at our notes before, or do you just want us to go in cold turkey and see what we found?
I would recommend.
what do you mean?
Oh, when you do the FRQ,
Yes.
I would make it a test situation.
Not bad to go to cold turkey. And can you do it a second time?
I mean, you could just do it on your own.
Yeah. I'd probably go with Mrs. Schrader there and say, see what you remember and get an idea of what you need to work on. The issue is, you know, what
I
if
wouldn't sit there and
they feel they
Google
can't answer
stuff.
things? That's a little bit tricky.
Hi.
So we can talk about that. Hello. All right. So if you wrote 1.57, is that acceptable? Meters per second. I think that would be. That's close enough in terms of sig figs and stuff like that. I think that's totally fine. Okay. All right. Where are we here? So we just finished up part A. Okay. Any questions? All right. Part B, free body diagram. I don't know why this dot is so huge. The biggest dot ever. Now, there is something I very much don't like about this problem. I wish they would have said, consider all frictional forces to be negligible. Okay. There is an argument to be made that there might be some friction force between the table and the book. And it's kind of a weird one. It would go with the motion of the book, but whatever. They want you to ignore friction here. All right. And so look, free body diagrams, you guys should be pretty good at this because we go, hey, what planet is on? Earth. What force should we draw in? Okay. So we're drawing in our force of gravity.
Were you able to do this?
It doesn't.
And it's on a surface. So what's the next one we need?
The normal force?
Absolutely. Now, is there a string? No, no tension force. They should have said ignore the force of friction, but it would be pretty small regardless of the case. And then are there any hands or anything, feet pushing it? Nope. So no applied forces, no spring forces, right? So we're in pretty good shape. Do we ever draw centripetal force as an individual force? No. Centripetal force means net force. And we don't draw net force as some extra force in a free body diagram. Okay. So, Mrs. Schrader, let me ask you on the rubric, what are they looking for in terms of, are they worried about the size of the forces in this problem?
It says correctly drawn and labeled normal force, correctly drawn and labeled gravitational force, no extraneous forces.
Okay, so this would be full credit here. And they
Yeah,
gave
it
it
doesn't say
3
anything
points.
about- But then the next one you have to say,
Now, the next one is where you actually have to care about the size.
Yeah.
Okay.
Mrs. Sharon, Mrs. Jones.
okay, got it.
Okay.
They're putting it to you, so I can't respond to them.
Yeah, try and put them to everyone or direct message Mrs. Schrader because I'm not paying as much attention, but it says, how are we supposed to label the diagram? I was unable to label anything on my computer.
I think the easiest thing is you'd be doing this on paper, taking a picture and uploading it.
Yeah,
But again, you're gonna take the AP test in person on paper, so we're not gonna worry about it so much.
Hopefully you guys heard what Mrs. Schrader, did you hear what Mrs. Schrader said there?
Reaction signs?
Okay, so she's encouraging you and I am too. Probably a good idea to work these out on paper right now since that's what you're really going to be doing. And you can upload pictures of your work into this. We saw if you did that. So that might be your best bet, I think. Okay. All right. So this is where you got to start understanding motion very clearly because they try and throw you off here. At the lowest point in the circuit path, the book is moving only in the horizontal direction. Okay. In what direction, if any, is the net vertical force on the book? And this is where we got to remember that it's traveling in a circular path. All right. And in order to be traveling in a circular path, there has to be a net force at all points in the circular path. And where does that net force always have to point?
Towards the center.
Has to point towards the center. And so for this one, if we're looking at this right here, now I am drawing the net force. This isn't me answering the question. This is just me thinking here. As I go, that there has to be a net force, and technically FC is what we call it when it's moving in a circle, pointed towards the center because we have this circular path. Okay. And so the answer to this one is going to be up. All right. Let's see. Am I supposed to circle one?
That's confusing looking at this.
Up, down, no direction. Since
I think you had a check on theirs. They had checks.
oh, okay. Did you have a
And then
check?
they had to explain underneath in a box.
Okay.
We were able to check that. Yeah, so I can tell you.
Yeah.
Okay. Fair enough. Okay. So it's going to be pointed up. Briefly explain your reasoning in terms of the book's motion. Now they give you that, if you guys looked at it, they give you a good reasoning, but let's kind of go through that again, because it's basically what I was saying to you. This is an object moving in a circular path. In order to change the direction of an object, there must be a net force acting on it. In this case, that net force will be a centripetal force. And centripetal forces always point to the center of the circle. And that should get you through everything. Unless you're grading me right now and I lost the point. Did I lose a
you're
point?
fine,
Okay.
It says the direction of the net vertical force is up.
Okay. And then they go, they have a little fancy thing, I think, where they call it, they have like
It's always starts
a
up.
3-step process, right?
Yeah.
What's that?
Right.
If they, the last thing's a reasoning.
A reasoning statement. Claim,
Want me to read the reasoning statement?
I mean, this isn't bad stuff. Claim, evidence, reasoning. Claim is what you're saying the answer is. Okay. This is what's backing it up. And then finally, this is the part where I'm saying, oh, it's a centripetal force. They always point towards the center of the circle. Okay. Not a bad idea though, when you have to give an answer, because they do these ones where they're like, you have to check something all the time. And so this idea of claim, evidence, reasoning is a really good one to keep in mind. Did they teach that to you guys in AP, Lang, Lit, anything like that?
Yeah.
I
so
feel
you
like
just
I've heard
have,
this-
like 3 words.
I feel like I hear my students using this phrase from one of their AP
I hear
English
my
department
7th graders
classes.
using it, so you guys should
More likely to hear it from any of the history.
Oh, history ones. Okay. So there you go. Like A push type things.
Yeah.
Yeah.
Okay. And makes sense considering the same company that writes your A push exam is the same company that makes your AP Physics 1 exam. All right. Where am I? Someone's raising their hand. Someone I like? It's Patty. Yeah, we can recall on him. All right.
It's fine. No?
He goes by Patty.
Excuse me. I just have a question about the last portion that we were talking about with the centripetal force.
Yeah.
So I understand that when it's at the bottom, the force is going to be facing upward because it has to face towards the center. But when it's towards the right and the x displacement is either 30 or negative 30.
Stop. When it's towards the right, do you mean when the object is at the right?
Yeah, when the book and the bench are facing towards the left or the right. Sorry, I keep on saying it for some reason. Where would the net displacement force be? Like, because I know it has to point towards the center, but how would that impact the normal force and gravity?
So that's where it gets a little bit tricky. In this particular problem, this is why I don't like them ignoring this in this problem. If they were asking about that position at the far right, do you guys know what force would keep it from, which force would make it change direction? Well, the centripetal is the net force. And what Patty is saying here, I'm confused because the normal force will be up, the force of gravity will be down. How do you end up with the bench? What about the bench? Providing what? Friction force. Okay. So that would be a much tougher problem because you'd have to recognize there was a friction force pointed to the left in that case, Patty.
Okay.
I think
Okay.
just one good thing.
All right. That makes sense. That makes sense.
Making sure if you're, not that was there, but not using it in a written explanation, just making sure that you're always very clear.
Yeah. You hear Mrs. Schrader on this? Because I wanted to be very clear on what Patty was asking. I made him not use the word it.
Should never go on. Well,
Unless it's really obvious about what it is. But I like what Mrs. Schrader is saying in that avoid using that word because sometimes it's too vague, right? And you just got to remember what's clear in here is not necessarily clear to the person reading your work. Is a person who grades physics tests, I know sometimes I can kind of look and I think you're talking about the right thing, but then I'll see somebody else do something totally wrong that maybe you weren't even thinking about. And I'll be like, well, maybe that's what this person was thinking too.
But they're not giving liberty with thinking.
Yeah, they are definitely not giving any liberty on the AP test. If it is not clear, it's wrong. Okay? So just use clear words as much as possible. All right. So that was part B, right?
Yeah, now we have to derive.
Oh, now we have to derive. Oh,
Everyone's favorite.
everyone's favorite. Okay, so what are we deriving here? Where's the actual question?
Vertical force on the bench at the lowest point.
There we go. All right.
All right, this is where, yeah.
Deriving algebras for the vertical force that the bench exerts on the book. Okay, that's a funny way of saying what?
Very good.
That's a funny way of saying the normal force. They like to do this on the AP test, by the way, sometimes. Instead of just calling it the force by the name you're used to calling it, they use the object A acting on object B terminology sometimes. And here they're doing it because they don't want to give you a clue that in the previous problem you should have had normal force. Okay? So even if you put the normal force though, you have to make sure you understand that's what they're talking about here. Okay? At the lowest point of the circular path in terms of the book's mass, great. Tangential speed, VB, radius R, and physical constants as appropriate. Do not substitute any numerical values for variables or physical constants here.
That means they
Okay.
leave C.
You don't need to calculate it.
Don't put 9.
Nope, you do not need a calculator. That is correct. All right. So, you know, it starts from your free body diagram. We've got this. Hey, what's that really important formula? One person.
Come on.
Thank you. Ma. Okay. And so what I've got to be careful about here is this time it's an FC. Okay, I'm going to write that instead of F net, even though it is an F net. Just a fancy way of saying it. And then we have the mass of our object.
It's just saying that C on the text.
What's that?
Yeah,
Oh, you
yeah.
can write F net. It's not wrong.
No, I
Okay.
was just saying, could you write FC and still?
Where? Like,
Instead of that.
if it's appropriate, it's fine.
Okay.
That's fine. I mean, I am. So they know what FC is. They know that that's centripetal force. Now I can't leave it like that because FC is not an allowed variable. So
Yeah.
in the long term, it really doesn't matter anyways.
I would say
Okay.
based
Yeah.
off the rubric here, though, you should have that first statement that he wrote, because one of the points is for correctly applying Newton's second law.
Yeah.
So if I state, that is one point that is highlighted there. So if you have that, and then you have that does equal FC, that's fine, but just starting with FC, I think you might lose out on that first point.
You
Okay.
might be able to write FC equals MAC.
Right,
That would not be incorrect. That's still Newton's second law.
right.
They need to see that you're doing Newton's second law.
Okay.
Always, you need a starting point. Okay, think very formally of a mathematical proof, and you go, blah blah blah. My postulates, if this, blah blah. You start somewhere. You can't just jump to the answer. Okay. Can you remind me what's my M here?
MB,
Okay. Lowercase or upper?
lower.
Do be careful about lowercase and uppercase variables, just like your password sometimes, case sensitive. Okay, they want you to use what they're given to you. And then I'm going to replace, actually, let's do that later. I'm just going to call that AC for right now. Okay, and so positive direction, negative direction. My up pointing force is the normal force. So this is the force we're going to be solving for. You can call it the normal force, but all that stuff that's equal to has to have the stuff that they're asking about. Okay, go ahead.
So he wrote the like plus and minus versus.
Mhm.
Do they know that, or can I do that?
You can do what he has up here, you can just write, normal minus.
They'll know what's
MB
going on
is
here.
fine as well. So did you have it written down?
No, I
anywhere?
didn't do the promote.
You did the what?
I didn't do the promote.
Okay. Where did you start?
This is.
And then I know I can't have
I'm
AC,
thinking that is
so
exactly
I'm just
right.
replacing that, right?
Yeah.
And what's my variable for V?
VB, lowercase.
And then capital R.
Capital R.
So what I've done, just to
Wait,
make
that's
sure
right.
people are following me.
Delete this word.
Oh, ugh. Sorry.
Move it up.
Thank you.
Perfect.
Don't be dumb.
We were testing it.
Look at your formula. Okay. So I'm just replacing AC. I initially replaced it with a formula that does not exist, which means you might want to check your AP formula sheet just to make sure you're doing things right. And go from there. Okay. Now, I think I'm in all my correct variables, aren't I?
Yeah. So now you just have to rearrange.
If you want to factor it out, you could factor out the MB. You don't
And
have. But
They do show that factored out, but.
Oh, they did?
Uh-huh.
But it's not, I'm pretty sure that this is gonna be. I think you get full credit for this.
Yeah.
You can factor it out if you can't factor out MB if you want. But this is how I would do it. This is one way of doing it, I guess I should say. So look, sometimes though, this one's not too bad if you recognize it's a FMA situation. But if you don't recognize that, you're probably screwed. So, but hey, what is my clue that I'm doing this? What are they asking me to solve for? The size of what? The size for the normal force, the size of a force. I mean, we haven't been talking about energy or momentum, so it's not like we're looking at work or impulse right now. How do we solve for individual forces? Come on. Okay. What's that?
Patty has a question. Then I
Go, Patty.
I'm just confused about why the radius is on the denominator because I initially had that portion correct, but when I saw the radius was on the denominator, I was thinking about how if the radius is 0 and there's no x displacement with the book and the bench, then you're dividing the values by
Is
0.
it cold outside, Lola?
A little.
Okay.
But anyways, okay. So why are you thinking radius is 0?
I was thinking about like how it would be applied to different parts of the system when thinking
Okay.
about the other answer below on part D.
Okay. So remember when we do circular motion, we're not, you're getting yourself confused with the graph that they gave you. They gave you a graph of the horizontal motion. There's absolutely no problem in looking at that. But when we're looking at the circular motion formulas, we don't break it into X and Y components at all. Okay, so when we're doing V squared over R, it doesn't matter where that object is. We don't look at like the X component or the Y component of radius. It's just the radius of the circle. Okay.
Oh, okay.
All right. Part D.
All right.
Part D is a little weird, I thought. At the lowest point of the circular path is the force that bench exerts on the book greater than, less than, or equal to the weight of the book. In a sense, I kind of feel like they asked this question already. This is just asking the same question in a different way. Because they're asking about whether this force is bigger than the force of gravity, equal to the force of gravity, or less than the force of gravity. But what do we know already from what we were talking about? What does it have to be? Well, if there's going to be a net force up, though,
Hi.
it has to be greater than.
But it's not accelerating upwards.
Oh, but
Yeah, that would, that's tricky.
so you can't get thrown by the circular motion. This is the changing direction acceleration. Okay.
Oh, yeah, that's.
And to be fair, if you think about this, it is here, right? And a little bit later, it's going to be here. Did it move up?
Yeah, but
It did. But it also had that motion in the other direction. Actually, I think I have it going the wrong way.
I think you can also
But that
think of the normal force as the effect of the full wheel on the book,
As opposed to,
as opposed to just the force directed upwards on the book.
I guess, I mean, the bottom line is that normal force is only coming from the atoms that are in the table underneath the book.
Oh, yeah.
So, but the bottom line is that normal force has to be bigger in order for there to be a net force pointed up.
so changing direction is also acceleration.
Yes, because remember, acceleration is defined as change in velocity over time, right?
Yeah.
Don't forget the over time part, by the way. People sometimes say acceleration is the change in velocity. No, it's not. Acceleration is the change in velocity over time. But what I'm getting at here is that velocity part. And velocity is more than just changing your, changing your velocity can be more than changing your speed, because velocity is speed and direction. Then we can also change the direction and have an acceleration. Okay. Any more questions on this one? Hey, I finished.
Yeah,
Mrs. Schrader's
We
proud
didn't-
of me.
I have the extra papers for the short day then.
Okay.
Anyone need me to look at any of those? You got it? Right here today.
All right.
Yeah, go ahead and submit your score if you just scored yours.
How'd we do?
5 out of 12.
That's hard.
It's a good one. That's not bad for a first problem.
If I had figured out to use Vermont, I would have got more like 8 or
Okay.
9, so.
We thought a circular motion one would be a good one.
It's got a free body diagram.
All right.
and-
How about you guys online? Anything else?
I made the mistake of misinterpreting normal.
Okay. Well, I think we're gonna call it
I have a
wraps then.
question.
Oh, sure. What's the question?
So for like the AP exam, will they give you like sheets of paper and then that's kind of where you put all of your work and all of
Yes.
your answers? Or okay.
And they give you they give you a good amount of space on the actual AP exam.
It would look like a normal. test.
Okay.
Yeah. Yeah. So I would say just like we try and give you enough space when we give you a test, they'll do the same thing. Anything else? Okay, everyone. I will see my students in class. Have a fantastic rest of your day. We'll push the recording up pretty soon. See you later.